Thank you very much. I'd like to thank a lot the organizers for the invitation. It's a great pleasure to be at EHES today, and it's a great honor to be the first one to speak at this mathematics for and by large language models workshop. So my name is Amaury Hayat. I'm a mathematician. I'm a professor at École des Ponts ParisTech. And as you might have guessed from the title, if I have to choose between mathematics for and by large language model, I'm more on the by side. Meaning that what interests me is to know how large language models can help us mathematicians to prove new theorems. So today we're in a world where we've all been using AI tools for years, sometimes without even realizing it. But something's changed, and I think the reason we're here today is because a year and a half ago, large language models started to be available for the general public, and with this came a new awareness of the impact of AI, awareness of the general public, but not only, also of scientists who started realizing that these could be helpful in their field. So this made the research with LLMs, or for LLMs, not only a young area of research in the scale of science, but also a very large area of research with different researchers' profiles. Some have been there since the early ages. And I can only encourage you to stay until the end of the conference to hear the last talk from Gabriel. And some I've joined in the last years. That's my case, for instance. So some design LLMs, other use LLMs. In any case, this created a very diverse community of researchers coming from different backgrounds, from computer science to physics to mathematics and so on. So I think this is really precious. And I thought that right before starting, I will tell you how it worked for me. I mean, the very first time I seriously considered using AI methods to prove maths were in 2016. Like many people, I just read the paper of the AlphaGo team and thought, oh wow, it looks great. I mean, if we can do this with Go, can we learn how to play math? Then by the end of 2017, I had lunch at Facebook AI with two friends, Alexis Cohn and Guillaume Lampe, and I realized that I wasn't the only one on Earth, and that Guillaume Lampe was also seriously considering working on this. And we thought, okay, let's finish our PhD and then see. And we ended our PhD in 2019. And then I received a text from Guillaume Lampe the day before his defense telling me, okay, I want to show you something. That was a paper he did with François Charton, who is here. And so that's how I got on board. So my talk today will be in two parts. I will first try to convince you that LLMs are already useful in mathematics today. In the second part, we'll look at a more prospective question, which is, can LLM prove theorems, and if so, how? So let's start with the first part. And I'll start by saying that, as surprising as it may seem, we've been using computers to prove theorems for years now. One of my favorite examples is this one. It's a conjecture of Euler of 1769. Of course, they didn't have a computer at the time. What Euler was thinking was that if you have k+1 integers and then the sum, and then if I manage to make it work, and the sum of the k first to the power n is equal to the k+1 at the power n, then the number of terms in the left-hand side has to be larger than the power. So that was a conjecture, and he wasn't able to prove this, and no mathematician was able to solve the problem, meaning prove it or disprove it, for almost 200 years. This was until Lender and Parkin arrived in 1966, and they solved this problem in probably the most silly way you can think of. They tried a bunch of combinations with computers, and they got this. You see, Euler said that on the left-hand side you need to have more terms, number of terms need to be larger or equal than the power, so you get 4 terms. 4 is not larger or equal than 5, so this is a counterexample. And this was also the only math paper I know of that can fit on one slide. So more seriously, this was a new mathematical result, but that was mostly the proof that even when you're a genius like Euler, you can still make mistakes. The only problem is that mankind take 200 years to spot your mistakes. So a more recent example is the proof of the Keller's conjecture in the last case that was remaining at the time. So this was proved in 2019 by 4 researchers who managed to reduce the problem into checking simple cases. The problem is that, so the checks are simple, but the number of cases is finite, but extremely high. And so they use the computer to solve this. So when I say that the number of cases is too high for a human, at the end of the day, if you look at the proof, you're not even asking how many pages is the proof, you're asking how big is the proof, and the answer is 200 gigabytes, which is about 10 times Wikipedia. Definitely something we could not have done this way, at least, without computers. So computers have been used to prove theorems for a long time now. But in these examples, the computer is doing a very easy task, just that you need to do it many, many times. So what we really want to know is whether LLM can be useful to solve more complicated theorems or more complicated problems. Oh, okay. Is it fine or? Okay. Okay, sorry about that. So problems where the difficulty is not just combinatorial. And in this case, so this is what we wanted to try. And I'm going to try to convince you that the answer is yes, with 3 different problems coming from different areas of mathematics. The first one is coming from stability of dynamical systems. So let's consider a dynamical system or a set of ordinary differential equations, like this one. So x prime is equal to f of x. Just going to remove this for a while. And so as you know, this can model many things. I mean, either in mechanics, this is a very simple example, in chemistry, in economics. So essentially, let's have this system, x prime is equal to f of x. And the stability question is the following. Is it true that for any epsilon, there exists a delta such that if the initial condition is smaller than delta in norm, then the solution of the system will exist for any time, and it will always remain smaller in norm than epsilon. So in other words, are all solutions arbitrarily bounded if the initial condition is sufficiently small? Or if I make a drawing, I mean, it's like this. You'd like to guarantee that for any red ball, there exists a blue ball, such that if you start in the blue ball, well, you don't pretend that you know what the solution will be doing, but at least you know that it will never exit the red ball. That's what you're trying to show. So this is a problem that has been studied for a long time. You can think of the work of Poincaré with the 3-body problem. And it has interested mathematicians for over 100 years. And thanks to Liu Xinxin and Netflix, it has also interested the general public for about 3 weeks. So a great advance in this field arrived at the turn of the 20th century with the work of Lyapunov, and in particular the Lyapunov functions. So what Lyapunov said is the following. He showed that if you can find a function that is strictly minimum in the equilibrium, so here 0 that you're considering, goes to infinity at infinity, and verifies this weird condition on the scalar product between the gradient of the function and the dynamic of your system, in this case, your system is stable. The answer is yes. So it's a very powerful result, because to answer yes to the problem, you only need to find the Lyapunov function. Now, there's just one tiny detail. This tiny detail is that nothing tells you how to find the Lyapunov function. And as it turns out, this is actually not a simple problem. For instance, if I show you this system and I ask you, okay, do you think this system is stable? Well, I don't know for you, but for me it's hard to see that the answer is yes, because there is this Lyapunov function. And you might believe me or not, but this is actually a simple case, because the Lyapunov function is diagonal. So, I mean, a trained mathematician would likely find it. So it's a complicated problem up to the point that today it is, you can have a good paper. It is a paper that was published in 2011. You can have a good paper which shows that a specific system has or doesn't have a Lyapunov function. So it's a complicated problem, and today, more than 100 years after Lyapunov, it's still an open question. There is no systematic way of finding Lyapunov function. Actually, we don't even know if it is possible to have a systematic way of finding a Lyapunov function. So what do we do when we don't have the mathematical tools to find a solution? Well, we resort to intuition to try to guess a solution, just like we will try to guess a conjecture and prove it afterwards, which might not be easy, but maybe easier. So intuition is an important concept in mathematics, and in a number of cases, it resembles a kind of pattern matching, pattern recognition. You've seen plenty of examples, and this gives you an idea of how to proceed in a case you've never seen. So our question is, we know that neural networks are very good at pattern matching. Can we train a language model, not necessarily large, that's what I put the first L in between parentheses. Can we train a language model to have a better mathematical intuition than us? And for me, a mathematician working with Lyapunov function, that would be a shocking idea that a neural network trained for a few days could have a better intuition than me on the problem that I learned for years. But so we decided to try on this Lyapunov problem. So once again, the problem is the following. I give you a dynamical system, and you tell me, if it's stable, you tell me yes, and this is the Lyapunov function, right? You just don't want the neural network to just say yes, because then you can't check it. But if you have the Lyapunov function, then you might have a way to actually prove it. So this is what we did with François Charton and Alberto Alfarano since several years, but especially this year, we actually submitted the paper yesterday. So the procedure is the following one. First, you generate a set of, you need to train your system. So you generate a set of data, like of systems and associated Lyapunov functions. So this is what we call synthetic data, artificial data that we're generating. And if you want to know whether in a more general context, synthetic data are the good points and the bad points of it, you need to stay until the next talk of Julia Kempe, so just in 50 minutes from now. And then you encode the example in a language that the transformer can understand, and then you train the language model. So I won't detail the two last steps. If you want to know, you definitely should come to François Charton's talk at 2:30. I'm going to talk just a little bit of the first point. Because I'm telling you, okay, we need to generate a lot of systems and solutions, but how do you generate examples of systems and solutions for a problem that you don't know how to solve? I mean, well, one way of doing would be to use what's called a backward approach. So instead of finding a solution from the problem, the thing we don't know how to do, you create the solution and then you find the problem. So you would create a function as random as you can among positive functions, and then you create all systems that could work with this Lyapunov function. If you're able to do this, that's not a trivial step, but if you're able to do this, then you'll be able to create a data set. We mathematicians love to know what makes something work behind. What makes it work here is the fact that finding a Lyapunov function is a hard problem, but checking that a function is a Lyapunov function is a much easier problem. Not necessarily simple, but at least much easier. The limitations is that even with a backward approach, even with a perfect generator, it biases the distribution, and this matters. And once again, if you want to know why this matters, you should look at François Charton's talk at 2:30 p.m. I hope I'm doing a good job at advertising the other talks of this workshop. All right, so I'm just going to go directly to the results, and what we can say first is that it works. If you do this, the language model learns the mathematical intuition of a Lyapunov function. And what's interesting is that if you were to add just a few examples that are high quality examples, so like something like 50 out of 1 million, so it's nearly nothing, it does change the performance and it works even better. And when I say even better, at the end of the day, it looks like this. So I told you there's no general way of finding a Lyapunov function. That's not entirely true when you have systems that are polynomials with a polynomial Lyapunov function that can be written as a sum of square. So in this particular case, you have algorithms that can do this, deterministic algorithm that can do this. But as you see here, so that's what I call the source algorithms. Source algorithms are typically not as good on the different polynomial dataset that we tried than our language model. And of course, when you go to general systems, I mean, there's no method, but the neural network still have a pretty decent accuracy. So you might want to consider what's going on if you try on Mathematicians. So we tested actually my master students, first-year master students of the course of control theory on one of the polynomial datasets. So they had 10 minutes to solve one example, and at the end of the day, they got an accuracy of around 10%, which might seem not much, but then I tried with myself, and I got 20%. So that's not that much more. So you see that, as shocking as it might seem, the LLMs are far better than, at least than me. And if you think that you can be better than a language model, then let's talk. I'll be very happy to test and see. All right, so this is the end of the first example. In the second example, we're going to go a bit deeper in applied mathematics, this time in control theory. So control theory revolves around the question, if I can act on a system, what can I make it do? And of course, we want to do this with differential equations or partial differential equations. Here, we're going to look at a system that models, that's why I'm saying applied mathematics, that models the population of mosquitoes. So you essentially got the eggs, male, female, and sterile male. And what you can do is add some more sterile male into the system. so that the female won't make the difference between the two types of male, but they can't reproduce with these ones, and we hope that it will decrease the population of mosquito. That's typically something that is used in real life, in particular in Brazil, to reduce the population of mosquitoes. And there's something you can choose in the equation. That's this U here, the rate of mosquitoes that you're of stereo mosquitoes that you're putting in the system. They have factories of mosquitoes, and you can put some. The only problem is that you can't measure everything in this system because it's a physical system. You don't know how many mosquitoes there are everywhere. So what you can do is measure the total number of male and the total number of female. So the female that are fertilized and the other ones. And what you'd like to know is to find a function of those variables that is your control. So you'd like to find a function f such that your system is stable. Now you all know what a stable system is. And in addition, you would like the population of mosquitoes to go to 0 except the stereo male, while you accept epsilon, but this needs to be epsilon as small as desired. So this is really a mathematician thing. You need to be able to reach a 0.1 mosquito. All right, so can you find control F? Well, this is an open question. I was suggested this question by a famous French mathematician in control theory, and no one knew how to find a solution. So we thought maybe let's try with an AI. I mean, maybe an AI can suggest a solution, and then we'll see. So you could try with a language model, but it will probably be hard to train. So what we did is a bit different. We used a reinforcement learning approach. You discretize your system of equation in a well-chosen scheme, so everything is hidden in the well-chosen, but for ODEs, that's okay. You train a reinforcement learning model, and if it works, if it trains, you will have, at the end of the day, a numerical black box control. So not something that you would like to prove a theorem, but that's already something. And then there is a non-trivial step that consists in looking at this and deducing an explicit mathematical control. And then you have to check that this is a solution to your problem. So that's what we did, and the neural network trained. So you have a numerical black box control, and we thought, okay, let's just deduce now a mathematical expression, and the problem is that the black box looks like this. So I told you that the control is a function of two variables. So you have here the two variables. Here is total males, total females on vertically, and this is what the output looks like. This is what the function looks like. And I don't know for you, but for me, when I look at this, I don't see anything specific. But fortunately, I have a very good PhD student, and when he looked at this, he told me, you need to look at this in log scale, it's much simpler, and he did. It's much simpler in log scale. You see that you start having a barrier between two areas, and then you can make formulas for this, so they are a bit nasty, but there starts the job of the mathematician to say, okay, now what's supposed to be important in this formula? Why does this work? And at the end of the day, you can end up with a control that is not super hard, but can be written simply. But really, I would never have guessed that you need this ratio of logarithm to be larger than a constant that you can write to have something that actually works. What's funny is that it works. So this is a phase space. So what the solution does is actually oscillating a little bit and then going down to very few mosquitoes that are only stereo mosquitoes. The other ones are gone. And another interesting thing is that it works for any epsilon larger than 0, but if you try for epsilon equals 0, it doesn't work. Meaning that even with something as approximative as neural networks, you can actually see a mathematical bifurcation on this control. So why am I telling you all this where there is no LLM in this? Well, because there is this non-trivial step going from the black box to the formula. I mean, a lot of people have been doing reinforcement learning. Here, the problem is really getting something that will be a formula that you can show to be correct afterwards. So here it wasn't so hard, but for more complicated controls it would be hard. So maybe you could have, and you could train an LLM to do this. I don't have the answer to this question, but that's something I'll be very interested in looking at in the future years. So this will be my final example of this part, and I'll be very quick on it. It's an example in topology. So this is this time a paper from a team of DeepMind and the team of Jordi Williamson in Sydney. A paper that was published in Nature in 2021. The principle is the following. If you try to look at the abstract principle, you have mathematical objects, let's call them Z. They have two types of quantities, x of z and y of z, and you would like to know whether there is a link between x of z and y of z. So one thing you could try to do is to train a neural network to predict y of z from x of z. And if you manage to do this, well, it means that there is a link. you don't know the link, but at least you know that there is a link because you managed to train one to predict one from the other. And what you're going to do is that what you want to understand is the function that is learned by the neural network, and then you can try to attack the neural network and understand what's behind. So with this, they found in particular a link between algebraic, hyperbolic and algebraic invariance of nodes, and I believe, so this was a conjecture, I believe they proved the conjecture since then. I'm not 100% sure of this, but I believe they did. All right, so this was my first part. I hope I managed to convince you that LLMs are already useful in the practice of mathematics and can help solve difficult problems. They are trained to have a better intuitions on human than humans on specific problems. That's the way we're working on. So they have the intuition, and then you are actually proving that what they are doing is correct, not the other way around. And it works on problems where, yes?
Finish and then I'll ask my question.
Oh, sorry. It works essentially on problems where this intuition allows to bypass the difficulty of the problem. I mean, if you are on a problem where guessing a candidate solution is easy, but proving that it's a solution is the hardest part, then it will probably not be useful. Yes?
So the first problem, just to be more precise, you're not training on a big corpus of language, and then on your examples, you're training on your example.
Yeah, completely. Yeah, I should have mentioned that. On the neural networks that I'm showing here, all of them actually, they're not pre-trained models. They are language models that we train from scratch from our data. That's why they're not so large, because otherwise, just with 10 million examples, that will be.
You call them transformer models, or?
Yes, exactly. They are. Yes, yeah. Actually, at first I called them transformer models, and then I thought, okay, I'll skip the slide on presenting transformers. So yeah, definitely. All right. So in all these examples, the AI is useful. The models are useful. But in this case, the mathematicians are still doing the reasoning behind. So a question you could ask is, can an LLM prove a mathematical result on its own? Yes?
Sorry, for the last part, did you try different network architectures? Or?
Not much, to be fair. I mean, we tried different parameters from network architecture, but just François might have tried the LSTM before the transformers. No? No, okay, so no. The answer is...
Yes, the point is that LSTM usually work, at least on small mathematical problems. There's no big difference between transformer and LSTM. So everything you do with a transformer, you usually can do with an LSTM or variants of it like GRU and all that. So it doesn't seem to be, it's about a sequential structure. You cannot do that with an MLP, but it doesn't seem to be something specific to the transformer and the attention, at least for problems I tried.
All right, so yeah, I think it's mostly because since it was working, we didn't change much the architecture. We changed the parameters, but yes.
Just to make sure I understand. So you didn't train the models by learning mathematics in general, putting all the archive or anything. Just a specific problem.
Yeah, just the specific problems. We'll come on learning on not archive, but we'll come on learning on more generic in the second part.
Would it be interesting to do the same experiment by using a model that has been trained on language general? And
the thing is, the models that we're using, they are trained to output a solution in a very specific form. So they're only seeing equations, and they're only outputting Lyapunov functions, for instance. So if you give them a lot of text before, it's not completely clear that that is going to help much. Because what they're trying to understand is what's the pattern matching behind that represents the theorem that we don't know that we would like to find, essentially. We tried this on theorems that already exist, like Kalman theorem, Kalman criterion for controllability, try to make them learn something like this, and a bit more complicated theorems as well. And it happens that you can learn the theorem from the pattern matching, but really what they're trying to understand is the structure behind. So, yeah.
And did you use this on some geometry problems?
No, but that would be very interesting, and we're probably very interested in doing this. You know, we started working on this in 2020. So
control problems. And did you see what does Jean-Michel Lasserie on solving PDA problems,
yeah.
Machine learning, Jean-Michel Lasserie?
Yes, I've looked at some of Jean-Michel Lasserie's work. From my understanding, the way they're solving the PD is not exactly the same, because they're trying to have. So I might be saying something. I thought they were trying to have a good approximation of the solution, to know what's going on, rather than qualitative properties that are essentially symbolic. So yes, I think then the type of networks is different. But then looking at different problems will be very interesting. I mean, for any problem, control theory is probably not, stability and control theory are probably not the easiest issues that I knew both of them, and so we have to start somewhere. But it probably works better in problems where you know, as soon as the conjecture is the hardest step, especially if the space is not that large. I mean, space of dynamical systems is pretty large. It's infinite dimensional. It's not a Hilbert space. I mean, you don't have many things. Even if you have a smaller space, it could be easier.
There is Terence Tao. He said to me that he uses a lot of machine learning to.
So no, that's a very good question. So I've heard the same. Okay, so no, but yeah, I heard him saying this in a conference as well. Checking is where we're going to go to it. He's using Lean. I mean, he rewrote some of his proofs in Lean.
Also for IDs.
But yeah, I don't know what he's using for IDs. I know he's been saying it. I've absolutely no clue, and I will be, of course, very interested to know what he's using. I mean, it's the type of mathematician that is so far ahead that we're just trying to follow the footsteps. So, no, okay, then I'm. Yes.
Regarding the different functions,
yes.
Can you tell us a bit more about the dataset? I mean, how many samples?
So you can start to do something with a million.
For training.
For training.
And what about the
sorry, the speed or the?
No. You got, for instance, 99%.
Yeah. Okay. Okay, I'm very quickly going to answer. This is a dataset that has a distribution that looks like the train distribution. It was generated in a backward fashion, and it has typically. I mean, I think they have between 1,000 and 10,000 examples in the train set. The second dataset is something that is. I won't get into detail how we get it, but it's a more natural way of sampling them. It's more look more like what problems would look like for humans. And the last one, I mean, for non-polynomial, the only way we can build the dataset anyway is from a backward approach. So there's no question in this.
For the inference, how many examples you tested to get the 99?
Between 1,000 and 10,000.
And for the, I thought you was the training.
No, training is 1 million.
1 million. Okay.
Yes. For this result, is it zero-shot learning, or do you train the model with it?
Yeah, no, so we don't train the model with the forward distribution, for instance.
You said like, okay, I'm sorry for the question. You said like for the very last row for the non-polynomial, you get 50 samples because it's very hard to get.
I don't know. Sorry, the 50 samples are the high quality are more like the second line. This one line, okay. So what we do is that you can only train on your backward distribution and test.
Okay.
And then you can train on your backward distribution, look at the other distribution, take out 50 examples that you remove from the test set and add them in the training set, and you realize that it helps considerably the rest. They will, on this, related to these questions about the distribution, you should really stay up to François Charton's talk, 2:30 p.m.
So since you're already here, I want to spare you in the end to go back. Did you think of including negative examples of things that don't have a Lyapunov function to tell the machine this is like a bad case?
So we thought about it and never did for the Lyapunov function. We did it for controllability of systems, and then in this case we added. We never really. I don't think we had. We changed a bit the proportion and we tried 80% positive, 20 negative, and 50-50. It was marking better with 50-50. Never really went above that.
It didn't give better results?
I mean, for controllability, it gives definitely better results than if you don't give any.
Kind of model.
Yeah, on the Lyapunov function we didn't because our main point was trying already to have a guess of something. Then, if you want to discriminate between yes or no with a better accuracy, then you will need negative examples for sure. I told you we submitted the paper yesterday, so I'm very happy to get the questions because we know what we have to do next.
How did you encode it, the input and the output, these functions?
So,
especially not polynomial.
This is a fascinating question that I would love to answer, but I believe there will be the answer this afternoon, or...
I'm adding the slides.
Okay, so please stay this afternoon. No, I don't want to spoil the surprise, and if you can't stay this afternoon, come to me at the break. And but it's a nice way of encoding it in.
What was the architecture of the model? How many layers?
10, I'd say between 8 and 10 layers. 8 to 16 attention head, 640 dimensions, 640.
How many time was training?
3 days, 4 days, on 2 days. Yeah.
2 days on 8 GPUs.
2 days, 8 GPUs, something like this. 8 GPUs, 8 GPUs, 32 gigabytes. You don't need brand new GPUs. V100 are fine. I don't know. I know at Jean Zé they're actually giving them because they are too old. So.
And the thing is that the many GPUs are only there because the GPUs we use don't have a lot of memory. So the models fit on one GPU all the time. They're modeled with a few tens of millions to 100 million parameters. So they're small model, but it has nothing to do with Llama and those kind of things.
Yeah.
And the only reason why you might need lots of compute is in this case you have very long sequences which do not fit in memory, or you cannot fit many of them in memory when you train. So you need lots of GPUs to increase the batch size, but sorry, it's more or less a technical term.
How much memory? How many gigabytes you need?
32 gigabytes of video memory.
For one GPU, so.
For one GPU. So the modern things, the Ampere and all that, have 80 gigabytes, and you go much farther with that. So the only reason of having 8 GPUs here is just to speed up, so not to have to wait a week or 10 days. But you know, everything we do on 2 days would work in a week or two. If we had only one GPU.
You could do
you can do it at home almost.
You can do it one GPU, just wait a week, and so I think the way the conversational learning shows that you definitely have to be there at 2:30 p.m. Yes.
My question was almost answered as part of this conversation, but what are the sizes of the inputs and outputs approximately? Like how many tokens?
I would say less than 2,000 tokens, and usually less than 1,000. But this order of magnitude.
Yeah. Input is larger.
Yeah, of course, input is larger because you need the full equation. Essentially, you will pass the equation, at the end of the day, you will pass the equation like x1 plus x2 squared. So it's not exactly this, but it essentially amounts to this. So you rarely go above 1,000. You never go above 2,000.
Can you directly get the output, or do you need a chain of thoughts or this kind of?
No, we get directly the output. Actually, it outputs the output at once. You don't have the autoregressive fashion. I mean.
How long time did you came to come to this particular architecture? Did you try many other architectures that didn't work or something?
I would say the main question was most for us, how long did it took us to make this architecture work? So we didn't change the architecture along the way because we thought there was something in the distribution that we weren't understanding at first. So I say for the architecture a few days because we didn't change much. No, we did some experiments on previous papers to have the good number of layers and heads. It appears that this is the way that works. On making the distribution work, like 2 years.
How does it, like, I don't understand why the distribution took so long to figure out. Like, what's the hard part?
Well, the hard part is really, I mean, here I'm saying, oh, that's great, you can just sample a positive function and generate all systems with Lyapunov function with it. I mean, this line.
Okay, yeah. So to find so many, like, problem solutions.
Yes, and you'd like something to be pretty generic. But you also want something that is not transparent because, you know, if you take something where the Lyapunov function is written in the system, there's no difficulty in finding it. You really want to learn the math problem behind, not the generator. So that's why you're testing on something that is very far from the training distribution, because you want to make sure that what you're learning is not the You can also try to you know, you have a system, you remove one equation and try to guess a Lyapunov function. If you can make it, that's a problem.
On the, is it like, how much is the contamination? Like so many sample that are...
none, zero.
Zero?
Zero contamination. Okay. You know, that's helpful.
Okay.
No, for sure it's 0 we check.
Did you try your method to guess terms of series or something like this?
No, but actually someone suggested this to me.
Did something like this?
Okay. Depends term or series or recurrent series. There is something. I'm really advertising the talk of François Charton now. No, there was something about recurring series, more like things that were closer to IQ tests or something like this, and so not as complicated as actually guessing the terms of more complicated series, and worked pretty well. It would be nice to go to a higher level to see what are the limits. This was one of the first examples where you need to actually do some work on the distribution to make it work until the end, because otherwise the transformers were so good that that you didn't need anything else. So yeah, very good idea.
Have you tried something? So something to check is easy, yes? So
easier, let's say.
Okay, so if your system generate, for example, not quite correct solution, but you might generate several solutions.
Yes.
And then you can kind of try to...
Yeah, actually we generate between 1 and 50 solutions and try them. Not by hand. I mean, we have a numerical estimator that tries to see what will be the most likely solution.
And have you tried to enrich your trained data set by this solution? So iteratively train, you find some?
No. We didn't do any kind of reinforcement learning approach by enriching and keep. No, we don't have an online approach. Mostly because it was working already, so we didn't felt the need of doing it. In the second part of the talk, that would be then said the last third of the talk. Now that I will talk a little bit of it.
Yeah, very nice question. Do you see the paper of them about material discovery? Like they have some problem, and they have a data set, and they use the data set to bootstrap the data set itself using a neural network. So basically, it made me think of that. So basically, you have a data set of equation, and you can generate yourself the data set. And thanks to the information that you get using this this solution pool or whatever, you can create a new part of the data set that doesn't exist before, and you can enlarge your scope of.
Yeah, that's definitely linked with what could be done on this. So no, yeah. Very good question. All right, I'm gonna. No, but that's fine. I don't need to finish the slides anyway. So I'm very happy to get a lot of questions. So let's go to the second part. Can LLMs prove theorems? So the question is, can LLM find a proof for mathematical statements? Sorry. There are a lot of people working on this question. This is only a subset of the people doing this. There's a related question that I'm not going to look at today, which is, can we automate human reasoning? This is something that Thematic Hours is looking at. So if I were to tell you, what do? You want an LLM to find a proof to a math problem. I mean, and I say, what do? I mean, the very first thing that you might end up doing is just doing a GPT-like large language model to guess the proof of your theorem. So what does, very schematically, so this was something that was tried by two researchers of OpenAI, Stanislas Poliu and Ilya Sutskever in 2020. Actually, Ilya Sutskever is known from the general public by someone who fired Sam Altman, but he should be renowned by the fact that he's an extraordinarily productive and inventive scientist. And so they worked on this question. And when you're doing this, let's wonder what is a usual GPT model doing. So an autoregressive transformer, very schematically. Forgive me if you're working the field and think it's too schematic. Let's assume that you have a neural network that is trained to complete sentences. And you start a sentence, so it's in French, because I thought we were at IHES, so I could give a French sentence. You start by this one, chaîne tentrée. What the model is going to do is first take your sentence, then thanks to sample the density of probability of the next word, thanks to the training, then sample and the next word. So here, given that you have this hyphen here, the il is a very likely next token. So then the autoregressive part is to put back into the sentence, look at this again, sample density of probability, and so on. And at the end of the day, so here you have a lot of possibilities. I mean, the density of probability is probably much less piked than the first one. But because Chen tenterait-il de lever la moustiquaire is the opening sentence of La Comédie humaine de Malraux, and the sentence is at many places on the internet. If you train on the internet, it's likely that you will get, with decent probability, a sentence like this. At the end of the day, you will do the same on your sentence. The density of probability would tell you something like something that says the end of the sentence, for instance, a question mark. And so you have your prediction, and so you just get it, and this is your prediction. Now, if you want to do the same, so this is a 1-minute crash course on how it's working inside GPT-3 and 4, without the complicated part. If you were to do the same for mathematics, what would you do? You would have a math statement. So now you're giving a math statement. You're sampling the density of probability of the next step of the proof. You output the step of the proof. You put it back. So now you have your statement, first step of the proof. You're sampling density of probability of the next proof, and so on. And then instead of training on the internet, you might want to train on, I don't know, mathematical data sets or whatever. And so this is the way you get the proof. And at the end of the day, you just have to look, hopefully, you have your statement and some step of proof. At some point, the model will say, this is the end of the proof. And you just take the right column, and this is your proof. Now, if you have a way of evaluating in real time what's the state of the proof right now, so you have your statement, you apply the theorem, what do you have left to prove? You can change this a little bit, because now you have a statement, you sample, you look at the density of probability of the next step, you sample a step, you apply the step, so now you actually have computed how the proof is like I had something I need to prove, I apply the theorem, now I have to prove the assumptions, so this is the assumptions, and so on. And you hope that at the end of the day, you have nothing left to prove, and if you have nothing left to prove, you don't even have a neural network, you have nothing left to prove, you just say, I end my proof. So this is the way this was working. We can be skeptical about the fact that it works by saying, okay, if I just look at the next step of the proof, it's really it's not really going to help finding proof. When you're doing mathematics, you have a much longer term vision and so on. But on the other hand, if you look at the essays that are working by ChatGPT, who is doing the same with the next token, they are pretty good. Whether you're skeptical or not, yes?
Just a question. Is this human written proof? Or
we'll come to this in a second. So that could be trained with any kind of data so far. So that's a very good question. That would be the next slide. But right before, I'd like to say that whether you're skeptical or not about this, it can only work if you have enough data. And when I mean enough, I mean sufficiently diverse and sufficiently numerous, like enough in number and enough in diversity. I mean, if you're only looking at number theory, you'll never learn something from, I don't know, stochastic PDEs. And the problem is that we have very few data available, especially for formal data, because you essentially have two types of data. You have data that are in formal language, that are written in French or English or Chinese or whatever language you want to consider, the thing that we are doing in our everyday life. And you have data that is written in formal languages, such as Koch, Isabelle, Lin, Hall. And this kind of data, they have a good point. The good point of formal language is that if you train a neural network to prove something into a formal language, then it cannot bluff, because at the end of the day, you put the proof in the formal in the computer assistant, and it tells you yes, the theorem is proved or not. You can't cheat with that. Well, if you learn to prove something in English, for instance, it might be a point where bluffing the humans is easier than actually proving the results. You know, it's sufficiently hard to be a reviewer of humans. It could be even harder to be a reviewer of a neural network. So formal language has these good points. The only problem is that we don't have a lot of data in formal language. I think Lin has the order of magnitude is about 100,000 theorems. So it's a very large data set for a human. I'll never know all these theorems. But it's a very small data set for an AI, at least for this kind of for the large language models. If you want to know what you can do in this framework, with this simple framework, when you don't have that much data, you can look at a paper from Fabien Glöckle, essentially, who is here in the room, so you might ask him if you have any questions. And if you want to know more about Lin proof step prediction, you need to come to the talk at 5 p.m. and to stay the entire day, but I mean, we're having so much fun that why wouldn't you stay? So the second approach, I still have a few minutes. So the second approach that we try to look at with Guillaume Lampe, Marianne Lachaud, Thibault Lavril, Xavier Martinet, Gabriel Emner, Aurélien Rodriguez, and Timothée Lacroix, you see a large team that worked for 2 years on this, was to treat mathematics as a game. So exactly what I was dreaming of doing in 2016, looking at AlphaGo. Because, you know, so DeepMind had an article about AlphaGo that could beat any Go player. A year after, they introduced AlphaZero, which learn chess and Go against itself. So you don't even need to feed him with proofs. You just need to give it the rules. And at the end of the day, it's better than any humans. So we thought, okay, let's do the same. Let's give the math rules and then let the AI be better than any humans on Earth. The game that we're playing at is this one. You have a statement. You can make a move. So make a move means apply a theorem. When you apply a theorem, you have to check the assumptions. So I made a move. I have 2 assumptions to satisfy. I make a move here, nothing to show. I make a move, nothing, 2 assumptions. I make a move, nothing to show. I make a move, nothing to show. Then if you're able to do this and there's nothing to show at the end, then you won. That's the game we're playing at. There are a few difficulties, as you might guess. The very first one is, I would say, machine learning difficulty. Learning to play a 2-players game is much easier than a solo game. Because if you have a 2-players game, at the beginning you have different AIs that you initialize. They are pretty bad at playing chess, but you make them play once against each other. At some point, one is likely to win. So you know that this way of playing is better than this way of playing. You have at least some feedback. You can get some idea. When you're having a solo game like math, you have a lot of AIs. They are all very bad at math. You have one exercise that you would like to show. They're all bad. No AI proves anything. You don't have any feedback. End of the day. So it's really a difficulty. In chess also, when you play a move, you always have a single game. I mean, you move the bishop, you only have one chessboard. In math, you apply a theorem, maybe now that you have 2 assumptions that you need to satisfy. So if you don't pay attention, you might have, you will never do this as a human, but if you let an AI do, you might have an exponential number of things that you have to show. Also in mathematics, I hope you'll agree with me, maybe not, but then in this case it will be interesting. It's relatively hard to know automatically. It's already very hard to know in the middle of a proof if you're going to succeed or not. Unless you've already passed the steps that are the key steps. It's really hard to say with a high certainty, yes, I know we're going to make it after 10 pages out of 100. It's even harder to know it automatically, to have a computer criteria that tells you this. And in chess, you do have a rough estimate at the beginning. At least you can count the pieces, for instance. So all this to say that, and the last difficulty is that the number of possibilities is much, much higher in mathematics. I mean, the number of moves you can play is huge, because there's not only the number of different theorems, there's where you apply it, what assumptions you can introduce. I mean, you really can do a lot of things. While in chess, I mean, if you have 100 or 200 moves that are possible, it's the max. So all this to prepare you to the fact that we haven't been able to train a neural network to be better than any human being, fortunately. So what we did in practice, and yes, I'm going to stop very soon, was the following. Instead of having just one transformer that predicts a solution, we thought, okay, there might be something slightly better to do. You can have something that predicts a solution. So there, the 0 step, if you want to be better, is you can have something that predicts several possible proof steps. Then you can expand a little bit to see what's going on if you use these proof steps. And you have a second neural network that tells you, okay, this is easy to show, this is hard, this is easy, this is hard. So that if the step that looked the most likely to do is actually giving you something to prove that is impossible to prove, then you might consider doing something else. So this is the 0 level. Then we do something slightly more advanced but it's relatively basic still. You're seeing all the possible proof as a huge tree. And what you're doing is that you're exploring this tree in a way that first gives some weight to this supervised learning large language model that you've used. And the more you're looking at the tree and the more you're seeing whether you manage to prove or not results, you're taking this knowledge and you give it some weight, and this adapts the policy with which you're actually sampling the next proof step. And what you can do, and this goes back to your question before, is that once you have enough data, you can actually train in an online fashion the neural network because you're finding new proofs or you counterexample of proofs, and so you can use this to keep training more and more the neural network that is behind. I think I'm already past the finish time, so I'll finish very quickly. At the end of the day, what we can do with this, well, this was 2022, so in the age of mathematics, it was like yesterday night, but in the age of AI, it was a decade ago. So we are able to prove to have a neural network that prove exercise essentially at undergrad levels, or undergrad levels close to the lecture notes. From time to time, it's able to prove an exercise from the International Mathematical Olympiads, for instance, n. So 7 does not divide 2 to the power n plus 1. I mean, I guess it's a good exercise. I mean, I'm sure you can do it, but yes. So one last comment, which is that we were a large team. It took us a long time to a lot of people. The funny part is that those two, after this paper and a few months after this paper, they decided to launch a company, and they launched a company that is called Mistral, and they raised 100 million and then 500 million. So unexpected outcomes of research in mathematics. I think the perspective is now to try to add more knowledge and structure about the way you're looking at the tree. You need probably more reasoning. It could start with human reasoning. That will be already very good. Maybe we will never reach that, but it will be good to try. We could have add some more hierarchy to the task. Maybe you don't want to prove to predict every proof steps, but you would like to at least to be able to know what are going to be the key steps of the proof. That will already be very helpful. And because data is a very limiting factor, it will be very helpful to have more data coming from archive, from math books. And right now, it's very hard to go from this data to a formal data that is actually completely proved, just because we are skipping a lot of steps when we're proving things. And this is something that on which a lot of people are currently working on, and we're also working on this. I hope I convinced you that LLMs can be useful in the practice of mathematics. I believe this is only the beginning. I also believe that the practice of mathematics will probably change, maybe not in the years, but decades to come. And I think that's okay, because it has changed a lot since the early ages of mathematics. There used to be a time where finding the digits of pi was a very large area of research. It's less a strong area of research today. But after all, is it really bad that things are changing and we're looking at new things? So I believe that AI will definitely not replace mathematicians, but enhance them. But I'm happy to debate about that. And I thank you for your attention.
We'll take a few questions.
I have a question. Like when you said that you have a neural network that try to predict the next step, on one neural network that try to see if the next step are good or not, right? Mm-hmm. Do you use the same network or not?
No. I don't know, they're trained differently.
Is it like like actor critique or?
Exactly, it's a policy and critique.
Okay. On the do you have shared layers between the two or not?
In what we were doing, not even.
Not even, but because is it not inefficient because they want to learn kind of a little bit the same thing?
Yes and no, because the critic really wants to learn the score at the end of the day. To be fair, we had a lot of trouble teaching the critic something that would work. Mm-hmm. For instance, when we were saying once you get the proofs, that things you manage to prove and other things, you'd like to pass this feedback to train your critic even more. Mm-hmm. And in fact, it was only helping to give the positive examples to the critic. It wasn't really helping to give intermediate scores. So, yeah, maybe that would have been, the engineering part of this was already.
Did you try? You said you use so much data. It was not pre-trained. It was only on the.
Yes. So this one today we will not do this like this because it was 2022 before ChatGPT and all these. So. There were no pre-trained model available of this size. So we had 0.7 billion parameters, which is considered very small today, which used to be huge at the time. So we were trained from scratch, first on synthetic data that we generated ourselves. that, to be fair, we have much better generators now. At the time, it was pretty crappy. I mean, that was. But you need to remember that when we started, like in 2020, mid 2020, the state of the art of theorem generation by AI was getting theorems like for x in a real number, sine of 3x is real. Like that was essentially the theorems you were able to create, which yes, that's definitely a theorem that is not in the database.
So now, if you continue this research, you will use pre-train with that?
Yes, for sure.
Okay.
But it was pre-trained on archive, even the old.
Yeah, right. At the end of the day, we ended up pre-training on archive because we saw that GPTF was pre-training on archive and it was helping. Yes, for sure.
And do you use Llama or do you use your own pre-trained model?
At the time, it was our own pre-trained model because this model became Llama.
Okay.
So I mean, yeah. So there were different people in Llama. I mean, it's just this model was the very first experiment that ended up being what became one of the teams of Llama.
One more question?
So can you elaborate on this last part with the cost function? Now this reinforcement learning framework, how do you evaluate whether
Yes. So yeah, what exactly you what we're doing? Okay. When we're expanding and try to see with the critics whether things are going to be hard or not to show. One thing you can do is to say I expand, and if I see if there is nothing to prove, it means that I solved something. So I put 1 as a value for this. Then here I have a critic model that's going to tell me the value, the probability of success, essentially by taking. So I say I have a probability of success of 0.5. Then I multiply the two, so I say the probability of success of this is 0.5. No, sorry, this was proved because you have one way of proving it. So let's go like this. This is 1, this is 0.5 probability of solving it. So 1 because we solved it, 0.5 because that's what the critic tells. You multiply the two, so you say, okay, this one has probability 0.5, this one had probability 0.4, so I said this one has probability 0.4 and so on. So you can get a value for your goal. And at the very beginning of the exploration, you're going to give more weight to what the supervised learning will tell you to do, because you haven't explored anything. The more you explore, the more you're going to add some weights to the thing you've already explored and to the experience you got. And the experience value is this one, the one you get by just multiplying in a very basic fashion. I mean, you have the model gives you a value. Either you succeed, either it's you succeeded. There's a way to prove the goal without showing anything. So you say this is 1. The value of this node is 1. Or you say it fails because this is an impossible statement. Then the value is 0. And in the middle, you use your other model to get the value, and then you multiply and gives you some values on the top.
Is it an average? If like there is one path that's going to succeed on all the other paths that's going to...
No, you just take the... If there is one, no, it's the max. If you have one, if you have one path that is going to succeed, it's 1. You know, I mean, it's like you say I have very different possible proof for this statement, but I know that 1 is correct. I mean, yeah.
One is extreme, but like 0.7 and 0.2 or something like that. It's like more like if you're, my point is if the 0.7 was a mistake by the network.
Yeah, I agree with you. I see what you mean. Yes, well, definitely something that could be changed or. The hardest part of this was to be able to deal with nodes that are not, those aren't trees, they are hyper trees, because when you have to satisfy two assumptions, sometimes they share the same meta variables. And so you can't prove one completely independently of the other. You know, when you want to show there exists X such that this and this, you can't show that there exists X such this and X such this. They have to be the same. So that was really the hard engineering part behind.
You check that there are some fundamental steps to go to the final proof?
Oh yeah. Well, at the end of the day, you consider it a success if you don't want to have a human looking at it. You want to be able to put it in lean, and then it says yes. It means okay. Yes.
Last question.
I have a question back to the Lyapunov function discovery. I was curious if you could interpret the model decisions to get some insight on how it discovers the function.
Okay, so it's going to be a quick answer. Essentially no, for the Lyapunov function. We tried for the contrariabilities. Honestly, I mean, I know the contrariability problem by heart. It's very hard to give a meaning to what it's doing. There's probably some coherence. There are some other problems that are simpler from math point of view, where it's possible, and I invite you to stay at 2:30 p.m. That's a running gag, right?
Thanks. Let's stop.
Thank you very much.